Hey, Gen Chem 1, welcome back. Let's do some more thermochemistry. I am so excited. I actually am going to tackle one of my favorite parts of thermochemistry, and that is bond energies. So it's very similar to what we've already been looking at, with one major difference. We are still going to calculate enthalpy of reactions. I love it. Let's write that down. We are still calculating that enthalpy of a reaction, but the difference is how we're going to look at it. When we calculated our enthalpy of this reaction, you'll notice I picked the exact same example from our last video. We have that combustion reaction, and I did that on purpose because I want to compare two different methods to calculate the exact same thing. But there's major differences in both calculations. So the first one we did was by reading our thermochemical table, and we wrote out here our enthalpies of formation, and that was for, then we subtracted our products, remember our products minus our reactants. And what we looked at was that whole reaction. So this whole process, this whole reaction. Okay, now that's awesome. That's really valuable information. That's what told people a couple hundred years ago, wow, methane would make a great fuel source. We can burn it and actually get heat from it and cook our pasta. So that's awesome. That whole reaction, it's telling us that overall that was going to be exothermic by 800 kilojoules. Wonderful. Good piece of information. Now, what if we actually wanted to break that down a little bit further and learn not just what methane is worth, but what about each bond in methane? Shut the front door. You know where we're headed. We are right back in Unit 2. Let's use our bonding rules. Methane is covalent. This is only going to work for covalent bonds. And do you remember in Unit 2, we started with just that octet rule, everything that followed our rules, and then we went sassy on top of that. We did formal charges, resonance, we did expanded valence. I'm going to stick with covalent bonds and the octet rule because that's where this works. So you'll notice in these, we're not going to have any of our sassy bonding, just straight up octet rule. So let's draw out our structures. Why would we care about the difference between our energy as a whole for methane versus maybe just one of these bonds? Well, if you're a chem major, and I know you are after we've had such an awesome semester, so I know you all are changing majors to chemistry. So as we keep going, it's really valuable information to tell in a chemical compound, well, what if these bonds are worth different energy? Well, the easier bond to break is going to be the first place a reaction happens. So it's very, very valuable information to actually break this apart even more and look at individual bonds. Now in methane, they happen to all be the same. But as we get into other structures, so like in organic chemistry, we would look at something like this. Well, now that CH bond has a different energy than that CBr bond. And then which one is the easiest to break? Turns out it's this one. And so that's exactly where our reaction happens. We can even predict that. That is our easiest bond to break. So it's really valuable information in later classes. We can also look at a whole reaction using bond energies. We just have to take a second to draw our structures, and then we're going to compare on both sides again. And what we're going to do is follow a simple rule. We are going to follow a rule that we're going to make all bonds and we're going to break all bonds. So you'll get yourself all kinds of confused if you're trying to just make and break one bond at a time. We are going to literally break all bonds and make all bonds. I feel like we need to write that down. So we are going to break all bonds, and then we're going to turn right around and make all bonds. Okay, now we're going to notice that our math is going to be a little bit different when we're using a bond energies table. because our bond energies table, let's switch to that. Let's find it. Our bond energies table, look at my numbers. There's no negative. You literally just have the value. Like for an NH bond, it's 391. It doesn't tell you if you're making or breaking. So we're going to read this table just a little bit different. We're just going to swap our math a little. I'll show you how to do that because there's no negatives on here. It's not telling you exo or endothermic. That's up to you. Okay, and remember in covalent bonds, we have single bonds, but then we also had double bonds. Double bonds are not just 2 times your single bond energy. They're actually different. If you were to take your CO and take 358 and multiply by 2, you're going to get a different number than what's being shown on our table. So you do want to read your multiple bonds on the multiple bonds of the table and single bonds on our single bonds. But I'll show you how to do that. Okay, so let's go back to our example. And then let's show you how we can read that. Okay, so what are we going to do? Well, first of all, remember, light a candle, find your balance. All right, we've got to have, I think we had to put a 2 here, right? And then a 2 here so that we were balanced. So then we're literally going to add up all of our bonds on both sides and then simply subtract them. Now notice this time it's reactants minus products. And that's because there's no negative on that table. So write that on your cheat sheet. When you're using your bond energies, you keep whatever's on your table, but this time you subtract reactants minus products. Okay, now we still do our moles and everything. So I'm going to literally add up each bond. We're going to break each bond and make each bond. So on this side, I have 4 CH bonds. And then I have that oxygen double bond. Okay, but wait for it. Don't we have moles there? Absolutely. We have 2 of those. So let's read our table for those numbers. Let's see what we've got. Let me find a CH bond. Let's find it on here and try to highlight it. This table is just a little bit small. Let me see if I can make it bigger. You know, I can't. There, we're talking turkey. Okay. All right, so let's look for, what are we looking for? A CH bond. That is 413. And then our other one was oxygen. So our oxygen double bond is 498. Okay, so remember that. In fact, I'm going to write it down. Okay, 413 and 498. Let's go back to our other screen. So that means we've got 413 here, except how many do we have? 4. And then we have, what did we say? 498 here, except how many do we have? 2. All right, bust out your calculator. Let's add those up. All right, I am getting 2648 kilojoules. All right, let's do the same thing on the other side. Okay, this is so much fun. And then we're going to compare them. We're going to subtract. All right, so we have, let's spell it out. We've got C double bond O. But how many do we have? We have 1 here and 1 here. We have 2 of them. In that molecule, you've got 2 of them. Okay, I think our table actually gives us CO2, so we'll have to double check that. And then we have water. We've got an HO bond. Okay, I love it. But how many do we have? Okay, watch this. You have 2 of them in your compound, but then you have 2 moles. So you need to multiply by 2 twice. All right, let's grab some data from our table. So we need our carbon dioxide. And see, it says down here 799 in, oh, I'm moving stuff here. I didn't mean to do that. All right, so it says here 799 in CO2. So let's write that down. That's 799 for CO2. And then we were looking for OH, and that is 467. Okay, so let's go try those. So I am going to write down then that 799 for carbon dioxide. And then for our HO bond, our hydrogen-oxygen bond, that is 467. Except how many are we going to multiply that by? 4. Okay, another most common mistake there. So bust out your calculator. Let's add those up. 799 plus that 467 times 4. I get 2667. All right, so let's double check that because we should actually be very similar to our first calculation. So if we're about to subtract those, I feel like I need to just do that one more time. 799 plus, let's parentheses, 4 times 467. All right, so now that's huge. Hang on. Yep. All right, 2667. So then if we are going to subtract these, let's see what we get. And then we better double check our math because it should be very similar to our first. Okay, I am getting a negative 19, but we know it should be more than that. So let's see if we can figure out where we went sassy, huh? So let's double check my calculations here and here. Okay, I've got a 4 times 413 plus 498 times 2. Yeah. Okay, and then our CO2 $7.99. Unless we have to multiply that by 2. Let's try it. This is a little bit different table for me because then I get 3466 because I had to fit it into the video. So let's try that, this number right here. And then we're going to write on that table so you know what to do with the 799. So do we mark that? Did they mean the whole CO2 or do they mean just the CO double bond? So let's find out. And this is how we're going to double check because 19 is nowhere near when we calculated it from the other table. So let's now subtract 2648 minus our 3466. Oh, shut the front door. There it is. Now we get a negative 818, which is very close to the first one. Put a sparkle pen around that. Okay, now let's go back to that PowerPoint and let's put a sparkle pen on what we do with that 799. That 799 in CO2 right here, let's write a comment that is only the CO bond. That is not the whole CO2. So you have to multiply that by 2. So we'll see CO2 again, and if you want to use this table on your test, mark yourself a note there. We have to, that 799 is just for the CO bond, not for the whole molecule. We still have to multiply that by 2. Okay, so let's walk through what we just did there. What we did was add up each bond, literally. Included our moles, On both sides, we added up those bonds. Let's make sure we put them ×2 there. And then we compared those two numbers. And what happens is that we had to literally put in that much energy to break all those bonds. But luckily, we got out that much energy when we made all those bonds. So overall, that first example in the last video, we calculated, we got an 801 kilojoules for this when we used our thermochemical table. So are these similar? Absolutely. Should they be similar? Absolutely. You're calculating the same thing for the same reaction. That's how you can double check yourself. Will they be exactly the same? No, not unless you get extremely lucky, but they're going to be very close. And why would they be slightly different? Because bond energies are an average. So there are many different CH bonds. That 413 is an average of those bonds. So that bond energy will be slightly different compared to, let's say, a different molecule with a CH bond. So if you've got something electronegative near there, that's going to change the energy in that bond just slightly. So our bond energies is a little bit less accurate. Your thermochemical table is more accurate, but your bond energies give you a different piece of information. They literally tell you, wow, that's really hard to break, because that's almost 500 kilojoules of energy you got to put in to break an oxygen molecule. Carbon dioxide, very stable. Look at how much energy you'd have to put in just to break up carbon dioxide. It's a very stable molecule. So you can, and then you could also gauge, like I said, your individual like CH bonds versus, let's see, a CCl bond in the same compound. Which one's easier to break? You don't get that information from your thermochemical table. So they give two different pieces of information, even though you ended up calculating the exact same thing, the enthalpy of your reaction. I love it. I'll usually try to word in the questions or on your homework which table to use, but if I don't tell you, you use either one. Use your comfort zone. All right, this is our same example too. So let's go through and let's see if we get a very similar answer to the last video. We should. All right, so let's start our process. Okay, holy crap, we have to balance this thing again. What did we have? I feel like we had a 4 here, right? And then I think we ended up with a 6 here, which would mean a 3 there. Does that seem right? 12 hydrogens. 6 oxygens, 4 nitrogens. That seems right. All right, let's draw our structures. So we've got to bust out our unit 2 and our bonding rules. 3 bonds and 1 lone pair to nitrogen. Our oxygen is a repeat. Yay. In fact, I even remember that energy. It was 498 kilojoules for that, to break that. Okay, then we're going to compare both sides. Okay, nitrogen, son of a, how do we draw the structure for nitrogen? There it is. And then water. We just saw water in that last video. Okay. All right, so let's start to add up our bonds and let's get some data. We have a nitrogen-hydrogen bond. All right, I'm going to color code. So we have 3 within our molecule. 1, 2, 3. And then we have 4 of them in our moles. So we need to multiply by 3 and by 4. So we literally have 12 NH bonds, okay? And then our oxygen, we have that number, that multiple bond number, we just have 1 in there, that 498, but we have 3 moles. Okay, so I'm going to write the 498 here, and we know we're going to multiply that by 3, and let's go get the NH bond. All right, let's look for NH. There it is, 391. All right, let's put 391 here, and then again, we're going to multiply that thing, holy cow, by 12. All right, so we're going to add up this side. Let's see what we get. You could get some pretty huge numbers here. That's okay. All right, I get 6186. Okay. All right, let's do the same thing on this side. We've got an N triple bond, so we better look under the multiple bonds. And then how many of those do we have? We've got 2 moles of those. And then we've got our oxygen-hydrogen bond. All right, let's do how many within the molecule. 1, 2. Okay, there's 2 of those. But then we have, holy cow, 6 moles. All right, so I think our OH bond, wasn't that 467? I want to write that skinnier. 467. And then our nitrogen, that's a new one. So let's look at that one. All right, where is nitrogen under our multiple bonds? It is, that's a double bond. We need a triple bond. So I'm wondering if that's what that is, and the bonds are just missing. Boy, this is a bum table, huh? So you may want to double check that. I'll maybe post a better bond energies, but I'm going to go with that 945, and we already know how to double check our numbers, right? 945, we know how to check it. So let's put that in there. 945. Okay, so we're going to multiply that by 2, and we're going to multiply this one by 12, and let's see what we get. All right, 945 times 2 plus 467 times 12. All right, I am getting 7494. I love it. All right, so you know what we do? We subtract reactants minus products on this one. And I get a negative 1310. All right, so was that close to what we had in that last video? I think it was. I think we were around the 1200s mark in that last video. So this is actually pretty darn close again. And then we know we read this table right if those numbers are pretty close. Now, my memory could be failing, but I thought we were in the upper 1200s for this one on the last video. So how do you know if it's close enough or not close enough? I would say within 100 kilojoules, especially when you're getting much bigger. It depends how big or small your numbers are. I mean, if we get into the tens of thousands and you're off by 100 or 200, that's pretty good. But if we're down at like 20, you want to be fairly close. But yeah, these numbers should be pretty similar. Again, are they going to be exact? No. But should they be similar? Yeah. And look, this is exothermic, just like the last one. So both of these examples, I love thermo because they look impressive, but you're really reading a table and adding and subtracting. We're doing pretty good that way. But we also are mixing in a little bit of all of our units. You've got to remember your bonding, or this isn't going to happen. You know, you've got to write out your structures in order to figure out how many bonds you've got. Could you shortcut? Sure, but I found over time, like I said, make all bonds, break all bonds, just do the whole thing, and then you're going to save yourself time in the long run when your numbers are nice and matching. So you want to try some of these. Remember, I'm not going to put any sassy bonding rules in there. You should follow straight octet rule. You'll notice my examples followed straight octet rule. That will throw off our bond energies if we've got resonance, formal charge, or expanded valence. So I'll keep the examples pretty similar to what we've done on this video. So you should have a whole homework of these. This should be in your homework, maybe not a whole homework, but you've got several of these. So how I word the questions for these, I will put in there to please use bond energies. And sometimes I'll ask you to compare, just like we did in this video. So I hope you enjoy.